Dear students, welcome to the third tutorial of the lesion to symptom mapping lecture, and today I show you something more special. You might remember that we got through lesion to symptom mapping in the tutorials 1 and 2, so today I'm gonna show you something that's not directly related to lesion to symptom mapping, but as I promised, I show you how to load and process brain images in MATLAB using SPM algorithms. To do so, well, you first of all need MATLAB, and as a student you can download it if you haven't already done so. You can go for the link I provided, and there you find a good manual that tells you how to install MATLAB as a student. Next thing you need is SPM. You can download it for free on the homepage on Software, SPM and Download form. And then you can select SPM 12, put in some information here and download it. You will receive an SPM folder, and this SPM folder you can copy it anywhere to on your computer. I just choose the MATLAB folder. Here I show you, this is the MATLAB folder on my computer, and I put the SPM file here. So this is the SPM file. There's one more vital part. We have to tell MATLAB where to look for SPM. That's the way of installing it. So you go here under Home on Set Path, and you click on Add Folder, and then you choose the SPM folder wherever you put it. And then this line should appear here, and at this point SPM is installed. Today we will not require SPM as used before with a graphical user interface. Today we just need some functions that are contained in the whole software package. Before we can work on brain images, it is necessary to understand what a brain image is. Let's go into MRIcron. This is also freeware and you can download it on the MRIcron homepage. If you download the file there, it is a zip file. Here you can download it, and you do not even have to install it. Just put the whole folder somewhere and click on the executable file. In MRIcron, you have several templates under File Templates. For example, this one, you might have seen it already. And this is a brain image. It is a T1 image of one single person. Now, this brain image, if we now go with the cursor through it and hold our left mouse button, you can scroll through it, but you will also see that some numbers up here are changing. There's a X, Y, and Z coordinate. So I've already told you there's some standard space that has coordinates, and each point in this image, each voxel is assigned a coordinate that you can see here. But additionally, there, up here where I have my mouse pointer, there are also numbers that change. Let's have a look at the numbers. If I click on this black area, it is 0. If I click on another black area in the ventricle, it is something very small, like 31. Now I can go to some darkish gray here. It's around 80. And I can go to brighter areas. It's 113. So you see, behind these grayscale values in the matrix, or in this image, there are some numbers. And that's all what a brain image is. It is a huge collection of numbers in a certain coordinate system, and the coordinate system can be transferred to a matrix, so a structure with 3 dimensions in this case that contains numbers. Now let's go to MATLAB. I provided you a script on Elias. You can open the script by going in MATLAB on Open, and then you simply choose the script. And this is the .m file. Here we go. It's called tutorial script matlab.m, and .m is just a common MATLAB file. Double click on it, and Here I provide you a lot of lines. Some are just comments that will guide you through the whole process, and some other lines where there's the actual content, so that MATLAB does something. The most important function today will be this one, SPM vol. This function opens an image header. So now you might ask, what is an image header? An image header is some kind of meta information in the image. So as I already told you, this is a large matrix of numbers, this image. But this is not everything. For example, MRIcron needs to know what is the resolution of the image. What is the maximum dimension in Z or in X direction? What is the point 0? Here somewhere. So MATLAB, first of all, opens this meta information thing. By the way, this meta information of the header were always contained in the Nifty files. Whenever I provided you some images in the last two tutorials, just like the ones now, the AAL, IFO, or PMAP, and the lesions here, each time I gave you the Nifty file that contained the image as well as the header at once. Now, let's get back to the header. In this example, I adapted these lines to a file I want to open. I want to first of all open a lesion file. I provided you some lesions in the zip file. Just unzip them anywhere. They are again all Nifty files, the same as we used the last time. And here you have to adapt the path where you put the files. This is just for my computer now. And here at this point there is a variable name. This is a name you can freely choose. It's best to choose something that makes sense, that helps you to remember what you did. So here I called it lesion header. I open a lesion file and it is a header. Now, if you type in this function, for example, by copy pasting it into the command window, you will find here that something appeared. You can either copy paste it down here, or you choose the whole thing and press F9. Works the same way. You can look into the header and you see that there are some information like the dimensions, the path of the file, or also here the point 0, the origin of the image. Now we do not want to work with the header, but actually with the image. This is the next line. And we see here now with the same dimensions as already found in the header, there matrix appeared. You can assess several aspects of the matrix like the size or unique images. Let's get to the unique images directly. You see it contains two different numbers that are unique, either zeros or 255. This is a little bit surprising. A lesion map is a binary map. It should be either 0 or 1. Due to some issues with data conversion, sometimes 1 becomes a 255 here. No problem, we can change this later, but we should be aware of this thing. Another very important aspect in anything you do in programming languages and MATLAB is that different objects can have different classes. You can assess classes with this function, class, and then whatever variable you have. And here it tells us double. Double is the format. Other formats are, for example, string format, single precision, double precision. This is what we have here, 8-bit, 16-bit, and so on. I can't give you a whole overview on all these data formats and what they're used for now. Just be aware of it, and if you're more interested or if you ever have any problems, just go for some MATLAB forums. There are a lot of explanations around. Let's get to the different examples. I provide you some examples that are quite close to practical things I often have to do in my work. The first thing is the task where we want to look at an atlas map. It is a probabilistic map of a certain fiber tract and the lesion, and we want to find out how much the lesion overlaps with this atlas map. We can look at this in MRIcron. we can open the lesion. It's this one, number 1002, and at the IFO. This is the inferior fronto-occipital fasciculus. So this bluish thing is the probabilistic map of the atlas, and the red thing is the lesion. And here you see there is some overlap, and in MATLAB we now want to find out how large is this overlap. What do we have to do? First of all, we have to use the functions that we just learned to load in the white matter atlas. It's done. And if we now use the function unique on this white matter image, we'll see that there are different numbers between 0 and 1. It is a probabilistic atlas, so for each voxel, a probability of being part of this fiber tract is assigned to. And this makes it a little bit problematic, these continuous scores ranging from 0 to 1. If we calculate an overlap of a continuous with a binary map, it's a little bit tricky. It's unclear what to do. So we go for a more practical way, and we binarize the whole map. So we just define that all voxels of this atlas map that are above a probability or equal to a probability of 30% are assigned to a binary map. This line does the job. And next we have to load the lesion. Importantly, here in this last line, I make sure that the lesion is actually a binarized 0-1 image and not something like 0 to 155. Now, how exactly can we calculate the overlap of two binary images? Well, here, so-called element-wise multiplication helps us. This is element-wise multiplication here, if we add a dot in front of the multiplication symbol. Multiplication of matrices does not help us here. It's something quite specific, rather complex, but element-wise quite straightforward. It just takes of two equally sized matrices, always the very first element in the one matrix, multiplies it with the very first element of the second matrix and puts it into a third matrix of the same size, and does the same with the second, the third, and so on until the last element. And in this resulting matrix, if we have a 1 in both images, so for example the lesion and the atlas map, then it will also be a 1. Otherwise it will be a 0, because at least one of the numbers in the multiplication is 0. And then we have a binary map of the overlap. That's what we want. So let's run this line. And now here, every overlap voxel is a 1. One additional information that I haven't told you yet, the resolution of these images is always 1 by 1 by 1 millimeter. So if we want to calculate the exact volume of the overlap, well, we just have to sum up all ones, and this is done here. And we see it's 2,651 voxels, so 2,651 cubic millimeters. Now, most often I do not apply just on a single lesion, but sometimes I have to look at a large database of maybe hundreds of lesions. This is what example 1b is about. Here you will see how to loop with a for loop through a lot of images and how to apply the same operation systematically again and again. I will not show it here. I think the explanations I provided you should be enough, and just try it out for yourself. Let's get to the second example. In the second example, we get to the so-called AAL atlas. You can see the AAL atlas in MRIcron if you go on the File, Open Template, AAL. And it is just an atlas that maps different cortical regions. Here you see, for example, supplementary motor area or the insula on the right, and each region has a certain color. Here. Of course, behind all these nice colors and the region names that are shown here, there are again numbers. Because it's a brain image, and brain images are always just some large matrices of numbers. We can load this AAL just like all brain images with the same functions. I provided you the AAL in the tutorial files on Ilias, but you can also find it in the MRIcron folder. Now, if we go for the unique elements in AAL, you see that there are numbers from 0 to 116. You can find these numbers again if you look at the folder of MRIcron. Here. MRIcron, that's the folder of MRIcron. And if you go on a template, you find a file called aal.nifty.txt, and here you find 116 numbers, and for each a region. So what is the task here? Imagine for some kind of region of interest analysis, we want a map of the right insula, this black area on the AAL. Now imagine we want a binary map without all this stuff here, without all the other regions. So this means we want a map where all voxels here in this black area are 0 and otherwise 1. How can we do this? We first of all look at the number for the insula here. The right insula has the number 30, and in MATLAB, after we've loaded the AAL, we can use this function to set all voxels that are 30 to 1. All other voxels are set to 0. So now there comes a critical point. We have to save this file. We want to have a look at this map that we produce. So in order to save it, we can use the function SPM writevol. It's this one here. SPM writevol requires a header and the image. The image we just produced. But the header, well, we looked at the header before and there were quite a lot of information inside. So how can we make our own header? Well, we go for the easy way. We just copy the old header that we already have. For example, like this. And we can look again at the header. What information is contained here? Well, stuff like, for example, dimensions or the origin, they can just stay the same, it's fine. But we might want to change the path, especially here the name. So change the name in the header, and this can be done by using this variable name. So it is the header, and there is some sub variable, and it's called fname. So type in new header, or whatever you want to, however you call this new header, .fname, and give it a new name, and then use the function SPM writevol, header name, and image name. Now, what did we gain from it? Now, wherever you put the path, there should be this file. You can open it, and now let's see. Yes, this is the very same AAL map that we've seen before, but now it's only, wait, it is only the insula here, and everything else is removed. Let's get to the third example. In the third task, we want to process a statistical map. A statistical map, for example, obtained in lesion mapping, is just a map that tells you for each voxel if it is significant in any mass univariate or any multivariate test. The map I provided you is called PMAP lesion analysis, and there you find numbers that are inverted. So a p-level of 0.05 is equal to 0.95, and the highest value is 1. This is equal to a p-value of 0. As that you know. You can load the statistical map just like any other brain image. And we can also again look at the unique elements of statistical map. And you see here there are some statistical values. Now imagine this is our statistical map and we want to binarize the statistical map because we want to perform a confirmatory fMRI analysis and we require a region of interest to do so. And we want to obtain the region of interest from a statistical map. And so what we do, we just threshold or binarize the statistical maps, and we want to keep all voxels that are significant at a value of p lower than 0.05. That means other way around, we have inverted values. We want to look at a statistical map and find all values that are bigger than 0.95. Let's do this. This function produces an image that identifies all elements of this matrix that are larger than 0.95. Let's do this. And just as an example too, you can save this image. Let's have a look at it. I called it binary stat map. Double click, and here you see a binary map. It's either 1 or 0, and it shows all voxels that were significant in, let's go to the original map, in this bluish map. But values like these ones that are below 0.95 were removed, and here it's higher than 0.05. Now let's imagine you do not want to produce a binary map, but another map, for example, for a figure. You want to depict all voxels that are significant and remove all voxels that are non-significant. But this time, you want to keep the continuous p-scores inside the significant voxels. How can we do this? Well, we already have the statistical map, the original one, loaded. This one can be done by indexing. This line is the indexing line, and what does it do? It looks in stat map. So this is the file where we save the image to, and identifies all elements that are smaller than 0.95. And these elements are set to 0 in statistical map. So each element in this matrix that is below this threshold will be set to 0. This is exactly what we want. Let it run and save it. And we can again look up the image. I close the old overlays, open the new one, and I called it mask stat map. And if we now rescale this image, for example, to ACTC scale, you see now there are different values in this map. There's still values like 0.99, like 1, but often something like 0.99, 0.98. So the continuous information inside this area was kept. So this was a tutorial on how to load and process images of brains in MATLAB. I hope this is helpful in your career, and I think many of you will work with brain imaging in the future, for example with SPM, and there are a lot of standard functions. For example, if you open the graphical user interface, these are often used in fMRI analysis and so on. And SPM has a mailing list. There you can just get the emails where a lot of people ask questions, and after some time I realized many questions could be solved just by programming stuff yourself. There are questions like, what is wrong with my header? So in the future, if you ever have problems because a function tells you something's wrong with the header, you can just open the header with these functions and look at the header yourself. Or some people want to get some regions taken out of atlases, as I've done, Right now, they want to produce some region of interest. This is a problem that is often encountered, and the standard functions might produce some errors. Happens quite often. As soon as you know how to handle the data yourself, well, you have this very powerful tool, and you're not dependent on anybody that helps you and who might have written the whole functions and really is into the topic. Well, just look into it yourself. I myself use these functions very often in my work. It helped me not only for some rather simple tasks like looking for all lesion data that I have available to find patients with a certain kind of lesion pattern or a lesion location, but also, for example, when I worked on multivariate lesion mapping. This was quite a new topic when I started in the field, and there were only some very raw scripts already available. So I downloaded the scripts, and because I was able to program in MATLAB and to open brain images, I could adapt it to my own research questions. So I hope you will profit from this information. I hope you use it one time. And if there are any more questions, feel free to write me some other emails and ask me.